we had limits. And limits are important. They're still important. You know, we still have to know how to do L'Hopital. We still have to know definition of derivative. And so that brings us to tangent lines. Now, we actually talked about tangent lines, which is, you know, what happens if you zoom in. So you have a curve, and it's doing all sorts of things. But if you say, well, what's it doing here? You say, well, let's just zoom in and take a look. And so you zoom in, and you say, aha, if I look there, it's a little bit flatter if I zoom in. If I can draw. Say, well, zoom in again. All right, okay. And you zoom in again. And lo and behold, it becomes very flat. And this looks like a flat thing. And this flat thing is our tangent line. Now, sort of the punchline to a lot of ideas in calculus are to say, curves locally look flat. And so we can use that idea. Now, when we think about a tangent line, I like to think of it as a tangent line is storing two pieces of information. And so they're spelled out here, but I'm going to write it down again. It's so nice, I'll write it twice. So the tangent line at x equals a, if I want that, that's the same as asking, what is the value of the function at a? What's the value of the derivative at a? And tangent lines are so fundamental to the subject that you just need to be ready. They're going to be there in some shape or form. So you just have to anticipate. A tangent line is going to show up. So if you ever say, oh, I have to find a tangent line, you always ask yourself two questions. Do I have my point? In other words, do I have my value of the function? Do I have my derivative? Do I have my slope? Now, tangent lines can arise in different contexts, and we'll mention a few as we go along. But once you have your point and your slope, then you have your basic formula. Y is the value of the function plus the derivative times x minus a. And what can we do with these tangent lines? Well, they will tell us local behavior, and we'll get into that in a little bit. But we can also use it for approximation. So whenever you see words like approximation, there are sort of two contexts where we had approximation. One was with Riemann sums, which was approximating totals, but we had other kinds of approximation. So for instance, we might have a linear approximation problem, and a linear approximation says, well, suppose I want to do something like estimate. So if you ever see estimate or give an approximation, all these mean the same thing, square root of 24. How would you do that? If you were, you're taking Calc 1, you put your Calc 1 hat on, how would you estimate square root of 24? Sorry, what?
Use 5 as your main value.
Okay, so you're saying this is really very bad approximation. Actually, not a bad approximation. It's really close to square root of 25. And square root of 25, we know. So the sort of the idea is like, oh, there's this function. Our function here is square root of x. And then what we can do is we can say, well, we know it very well. We can give a tangent line at x equals 25. And then we can use that to say, well, the function mimics the line. And so we can use the tangent line to mimic the function. So at x equals 25, f of 25, square root of 25, 5. Does anybody know the derivative of square root of x off the top of their head? Yeah, so square root of x is x to the 1/2. 1/2 comes down. 1/2 x to the negative 1/2. 1 over 2 square root of x. So f prime of 25 will be 1/10. 1 over 2 times 5. So This says that square root of x, which is our function, is approximately the value of the function at 25, which is 5, plus 1/10, the derivative at 25, times x minus 25. Now, it's not a good approximation everywhere, but where is it a good approximation?
At square root 24?
Well, it's a good approximation near 25, right? Your tangent line is useful near. Calculus works in the nearby. So, okay. So, what is square root of 24 approximately? What is this telling us? What's our punchline? Square root of 24 is approximately 5 plus 1/10 times -1. Our channeling our inner engineer is 4.9000. 4 digits of precision. Highly precise number. Now, is the square root of 24 4.9? No. Is it close? Yes. Is it good enough? Maybe. Depends. You know, are we just passing time with coconuts on a deserted island? It's a beautiful answer. Are we sending something to outer space? Maybe we should add a digit. You know, it just depends. It depends on how much accuracy you need. And depending upon how much accuracy we need, we have ways to get it. Now, there's another way this shows up, and I don't think I have it on another slide, which is tangent lines showed up in Newton's method. So what's the idea of Newton's method? We're trying to find root. We don't have root. We have a guess. So what do we do to make a better guess?
Use the tangent line of that guess in order to get closer to the root.
Use the tangent line to make a new guess. So this is next guess, xn plus 1. And so really Newton's method was no more than follow the tangent line. So tangent lines show up in several places in different contexts. So you might be asked to find a tangent line. You may be asked to use a tangent line. That's an approximation. Or you might have Newton's method, which is really just built off of doing tangent lines. All right, how are you feeling about tangent lines? Any questions? Okay. Well, no surprise, but we're going to have derivatives on this final. I know, a calculus final with derivatives. Wow. So make sure you know your derivatives. And there's more or less a collection of rules. And that's the nice thing about derivatives, is if you know your rules, you can take a derivative of anything that you encounter. So what are your rules? Well, you have your building blocks. So the derivative of x to the power k, kx to the k minus 1. And this is, by the way, well, we talk about square root of x. We write it as x to 1/2. We make it calculus friendly for the rule. The derivative of e to the x is e to the x. It's your favorite function. And when you take differential equations in a few semesters, you'll be like, man, they just love that e to the x function. And we do. It's just like the whole semesters. Have you tried e to the x? Oh, that works really well. And so make sure you know that. Know your log of x, 1 over x. Don't panic about absolute value. I don't think we care that much these days. There's always discussions we have when the graders and faculty get together. Should log have an absolute value or should it not? And I think we've come to the conclusion that the answer is, it depends. But, all right. Arctangent. Just know this one. Not because it's necessarily on the final, but because you'll need it for future semesters. It shows up in unexpected places. Sometimes we shoehorn it in there, but sometimes it shows up for legitimate reasons. And then you have your combining rules. And so no big surprises. You have that derivatives are linear. So that's helpful. And this basically says what? Break things apart. You know, don't, if you have a nice plus, and this is a nice plus, this kind of plus here, then that lets you say, hey, instead of doing everything at once, you can break things into small pieces. You have product rule. How do we handle two functions multiplying? Of course, you have chain rule. And I would say that when it comes to rules, chain rule is perhaps the most important rule. And you will use this many, many times in your future. So if there's only one rule to remember for derivatives, make it the chain rule. We also have various other things. We have logarithmic differentiation. This is a good one. And and derivatives of inverses. Let's see, what's a good one to talk about? Any questions about your basic rules? Can we try some functions? All right. And one other comment. It doesn't have to be x's. Sometimes they're t's. Sometimes there are other symbols. So be open to other symbols being there. Let's find a derivative of, say, 5 to the t, t to the fifth, arctangent of t. Is that enough? Should we add more? More? Okay, that seems like enough. All right. How does one do such a thing?
Quotient?
Yes, we can do quotient rule. Do we write it down? Nope. Should we write it down? For all those people who love quotient rules? All right. So the derivative of f of x over g of x is f prime of x, g of x, minus f of x, g prime of x, g of x squared. Now, we can definitely do this by quotient rule. What? Well, or we can do it by logarithmic differentiation. Which one do you want to do? You sure you don't want to do quotient rule? I kind of feel like we're in the quotient rule phase. Are you sure? Oh, come on. You got me all excited. I even wrote stuff down. All right. All right. No one wants that. All right. Okay, so if you're doing logarithmic differentiation, which is an alternative, then you have this rule. So it says, hey, this is the function 5 to the t, 2 to the fifth, arctangent of t, times the derivative of log of 5 to the t, t to the fifth, arctangent of t. Okay. But then what happens? And then you realize you didn't give yourself enough space on the page. But other than that, sorry, what? Yeah, use your log rules. Log rules are good to know. Just in life, you should know your log rules. Log of a times b, log a plus log b. Log of a divided by b. Log a minus log b. So multiplication becomes addition. Division, subtraction. Log of a to the power b. Exponentiation becomes multiplication, so that the b comes down. All right. So we have our 5 to the t, t to the 5th, arctangent of t, times the derivative of, what's log of 5 to the power t? T log 5. Yes? I'm just that part. Log of 5 to the power t, t log 5. Okay, plus log of t to the 5th becomes 5 log t, which is not the same as t log 5. And what happens here? Minus, because it's downstairs, log arctan. We'll pretend like we fit it in. Okay, so we're almost there. We're in the home stretch. The reason we do logarithmic differentiation is it helps us pull things apart. It also helps us when we have weird things happening, like a function to a function, or even 5 to the t. Does anybody know what the derivative of 5 to the t is off the top of their head?
No. G5 to the t minus 1.
It does have a natural log. Okay, what's the derivative of t log 5?
5 over natural log 5. 5t over...
Natural log of 5 is a constant, so the derivative of t times natural log of 5 becomes? What? Log of 5. Yeah, because log 5 is a constant. You know, this is like t times 8. Derivative of t times 8 is 8. Just a really weird looking 8. We call it log 5. How about 5 log t? What's the derivative of 5 log t? The derivative of log t is 1 over t, so 5 over t. Now, log of anything complicated, write a fraction. So if I'm taking the derivative of log arctangent, whatever is inside the log goes in the downstairs. So arctangent's in the log, goes downstairs. What goes upstairs? The derivative of arctangent, what rule are you using? Chain rule. What's the derivative of arctangent? 1 over 1 plus t squared. And there we go. All right. So just in case nobody caught it, what was the derivative of 5 to the power t?
Natural log 5.
There's a natural log 5 involved in the answer. What else is involved in the answer? What? Not t to the 5th. Five to the t. Now you can do it by logarithmic differentiation. Another way to see it, this is e to the log 5 t, right? 5 is e to the log 5, which makes this e to the t log 5. Now use the chain rule. When you take the derivative of e to the t log 5, what happens? The log 5 comes down. So that log 5 comes down, and you're left with e to the t log 5, which goes back to 5 to the t. Yes? No? Maybe? You're very skeptical. Or maybe it's just like it's the end of the semester. I don't know, Steve. Can you make it? Can we make it? We'll all make it together. All right. How are you feeling about your rules? Got your rules? All right. All right. Well, you have questions. Now's a great time to ask. Better to ask now than after the final. Okay, so our,
Wait, doesn't log to the e cancel out?
Yes,
But the e to the log doesn't cancel out.
they do. Are you disagreeing with something I wrote? We can like throw down. I haven't lied to you today. It's a good day. Well, you know, I try not to lie, but I know what I wrote down was right. I'm confident of that. Okay, implicit differentiation. Now, what is implicit differentiation for? Well, it's when you have a situation, such as here, where you can't solve for y as a function of x. So our differentiation rules are built off of, if I have y as a function of x, I have this wonderful machine. And so usually our rules for differentiation is you have this beautiful machine here, and you know it's the derivative machine. You toss in your f of x, and out comes your f prime of x, and life is good. And the derivative machine is what we saw in the previous part, the last page. But implicit differentiation says, hey, what if I don't have an f of x? Am I still able to put things through the machine? Well, kind of. What you have to do is be careful. So the key thing is to say, what if I'm faced with a situation where I cannot solve for y? So this is a place you can't solve for y, because one y is outside of this exponential function, one is on the inside of the exponential function. So anything I do that frees this y traps that y, and vice versa. So it's just they cannot simultaneously get together. So it's hopeless to solve for y explicitly. But they're still connected. So you say, so there's some way that they're connected. We just don't know what it is. So this is our great aha. We sit here and say, and we have a thought bubble. We say, I don't know exactly what the function is, but I'll say there is one. We'll just keep it as some unknown function. Well, x has the same problem. Here, you say, look, this x is outside of cosine, this x is on the inside of cosine. Anything that you do that gets the x outside of the cosine will trap this other x inside an arc cosine. It's hopeless. Hopeless. But it still means we can do stuff. So what does that tell us? Well, it tells us that in a situation such as this, when we look at it, we don't write it down, but we say secretly, this says you have some function of x plus e to the x times some function of x equals cosine of x plus 5x. What happens next? Sorry, what? Take natural log? Well, natural log does not get along well with addition. Natural log and addition they had a bad breakup many, many millennia ago, and they just never recovered. So just logs and addition don't mix. So remember, we're after y prime. So what do we have? We really have two functions of x. Now, if I throw a function of x into the machine, I'll get its derivative out. What if I throw that same function into the machine? What will happen? I'll get the same answer out. That's sort of the point, is there's a consistency of answers. So the derivative of the left has to match the derivative of the right. That's implicit differentiation. Let's take the derivative of both sides, keeping in mind that y is secretly a function of x. So let's start by taking derivatives. Now, we normally do not write this step down. This is in our head, but we'll point to it as needed. What is the derivative of y with respect to x? So here we're going to take d over dx, meaning derivative with respect to x. derivative of y with respect to x is dy dx or y prime. I like y prime because it's easier for me to write. But you can also write dy dx. What's the derivative of e to the power xy? Take the derivative of that with respect to x. Okay, good. Chain rule. So e to the, if I have e to anything, the derivative of e to anything is e to that anything times the derivative of the upstairs. What's the derivative of xy? What rule do you need? Product rule. Derivative, we'll do the derivative of the first times the second. Gives us, well, I'm asking because we want to figure, oh, you meant y. Oh, the variable y. I am so sorry about that. Yes, you're right, y. The derivative of the first times the second is y. Good. Plus the first times the derivative of the second. What will that be? xy prime. Okay, that's the derivative of the left equals the derivative of the right. What's the derivative of cosine x with respect to x?
Negative sine x.
Okay, I've heard sine x and I've heard negative sine x. Which one is it? Negative sine x. Yeah, be careful. That cosine and sine is, they're tricky. The derivative of 5x with respect to x. 5. Okay, are we done? No. Because what does it ask us to solve in this case? Y prime. So it's like, oh, you want y prime. Yeah, we do. Okay, so what does that do? Well, we can get y prime by itself. How many y primes do we have currently? There's 2 of them. So we want 1 y prime. 1 y prime to bring them all together. So we'll do things like algebra. We can distribute y prime plus e to the xy times y plus x e to the xy y prime equals minus sine of x plus 5. We can move that all the way across. What's left on the the left-hand side? All the terms have a y prime in them. So what do? Factor it out. 1 plus x e to the xy times y prime equals minus sine of x plus 5 minus e to the xy times y. So that tells us that y prime, which is another way to write dy dx, minus sine of x plus 5 minus e to the xy over y, divide by 1 plus x e to the xy. All right, cool. And there you go. Now you might say, why did we do that? I don't know. The problem asked us to. But maybe it was trying to build up to something. For instance, what does this help us do now? It helps us find slopes at points. So what if I gave you a point? What if I told you the following point? I said, what's the point on this curve? Does anybody see an easy point on this curve? Okay, x equals 0, y equals negative 1. That's the point on this curve. Why? Well, let's just check. When you plug in x equals 0, y equals negative 1 into the left-hand side, what do you get? Negative 1 plus e to the 0. Negative 1 plus e to the 0 is 0. And let's see, did I mess this up? I did. Yes. We'll change that. X equals 0, y equals 0. How about that one? All right. 0 plus e to the 0 is 1. Cosine 0 plus 0 is 1. So 0, 0 is a point on this curve. Okay. All right. What's the slope of the tangent line at 0, 0? Can we find that out? And how do we do it? So if I have a point, how do I find the slope of the tangent line? Find the derivative. Do we have the derivative? Yeah, we just worked really hard to get it. So what's left to do? Plug in. What happens when you plug in x equals 0, y equals 0? What do you end up with? Five over 1. So it says the slope of the tangent line at the origin is slope 5. Now we could find the actual tangent line if we wanted to. So that means that the tangent line, if we wanted to, we could just say tangent line is y equals 5x. All right. Implicit differentiation. Any questions about that? Cool. All right, related rates. This gets us into one of our two word problem type things. So, how do you recognize a related rates problem? Well, you'll see lots of rates. So if you see a lot of rates in a problem, if you see like, oh, there's a dx dt, a dy dt, a dq dt, I don't know whatever symbols. But once you start seeing lots of rates, you start saying related rates. So you say, okay, so if I see lots of rates, I look for relationships. Now, how do these problems tend to come together? Well, you've got your classics, you've got your Pythagorean relationships. So this is right triangle sides. And so this is your, a squared plus b squared equals c squared. You have your SOHCAHTOA type things. And this is if you have an angle. So if one of your rates involves an angle, then you start thinking SOHCAHTOA. Look for your right triangles. Think, okay, what sides do I know? And start thinking, do I use a sine, a cosine, or a tangent? You might have geometry. So this might be things such as lengths, areas, volumes. So in other words, you have some kind of geometrical thing, and you might be like, well, maybe I'm filling up I have a cube, and I have 3 dimensions, and 2 of the dimensions are doing this. What's the third dimension doing? Or I have a sphere, and the sphere is expanding at this rate. How quickly is the surface area changing? Things such as that. So that's geometry type things. And then, of course, generically you have just a formula given to you. But more or less, that's about the only things that we really encounter. And the first 3 are just special cases where we're able to derive a formula. When we talk about a formula, what that really is trying to tell us is that this formula, this is our relationship. So when we talk about a relationship, we're trying to find some expression that relates the variables together. And why do we like these problems? We like word problems. One of the goals that we want you to do is by the time you hit the end of calculus, we would love you to be able to think about translating real world into mathematical expressions. And word problems is an opportunity to do that. And there will be a word type problem on the exam. So just be open to that possibility. And related rates is one of the 2 classical places where we have word type problems. Another one is coming up, although at the rate we're going, we won't get there today. All right, how do you solve related rates problems? It's been a while. Yeah, drawing a picture can be helpful. So, isn't it good that we're reminding ourselves? So roughly speaking, step 1, find the relationship. Now sometimes if they give you a formula, it's like, hey, I found it, woohoo! Sometimes you have to draw a picture, but find the relationship. And when you talk about find the relationship, what you look at is you say, what things are changing? Those are your variables. So if I have, a length and a width and a volume, those are the things that are changing. I say, okay, I need to find an equation that relates those things. So when I talk about a relationship, I'm really talking about an equation, just to be clear. Now, after you found your relationship, what comes next? What? Take a derivative? Good.
You substitute in for the thing that's changing, so you have like one variable in your equation.
Well, you're thinking of optimization. That is what you want to do for optimization. So yes, that's a good tool in a different setting. And we'll talk about optimization. I don't think we'll get there today. But take a derivative. Now here's the thing. We're going to have another thought. What's our thought for related rates? Write down everything you know. That's a big thought. I don't think I can do that. So everything depends on t. That's what we think. When we see related rates problem, we say everything that can change is a function of t. So if I have x, y, and v are my variables, I say I have x of t, I have y of t, I have v of t. So everything depends on t. So we take a derivative with respect to t. And everything which can vary, you have to keep track of it. Okay, so that's your step 2. Take derivative with respect to t. All right, so we found a relationship. We took our derivative with respect to t. What's left? Plug in what you know. Oh, that's a beautiful answer. Yes, plug in what you know. And what else do you do? Solve for what you don't.
80.
And that's the whole process. That's it. It's not too bad. So related rates problems boils down to, can you find the equation, take the derivative of everything with respect to t, take your time, make sure you have the right rules, and make sure everything that is varying, you're treating like a varying function. Plug in what you know, solve for what you don't. And you're done. So these can be very quick, as long as you know the process. Do we have time to do one? There's an example here. Should we try it? All right, a fire truck has a ladder which is currently extended 50 feet and is extending its length by 8 feet per minute. And the ladder is designed to always maintain contact with the side of the building. Okay, so there's a building. So we make a drawing. Here's a building. Now you might say, when you look at my drawing, how do you know that that's a building? Because it says it. See how sophisticated your drawings have to be? Not sophisticated at all. Okay. So we have a ladder. There's this ladder here. Here's our ladder. Again, you're like, I see it. I totally am convinced by your drawing. Okay, so the ladder is changing length, right? Because it's extended, but it's also extending further. So the ladder changes length. It's always has contact with the building, and the ladder truck is currently 30 feet away, so there's this distance. and it's moving away. Okay, so this distance is changing. So this is, we'll call it our distance. Determine if the ladder is moving up or down the side of the building and also the speed it is moving. Okay, so we have, what scenario are we in? What case are we in? Yeah, right triangle. Unless this is one of those really weird buildings, you know. Was it Frank Gehry who had these weird, fun shapes? We'll assume it's not. We'll assume it's a normal building. Fun for the architect, not the engineer? Ah, someone knows how to engineer. Okay, good. So we have our sides. Let's give them names. We might as well give them convenient names. How about B for building, D for distance from the building, L for ladder. D squared plus B squared equals L squared, Pythagorean theorem. That's our relationship. Now, what's step 2 say to do? Take derivatives. Now, which one of these is changing? Yes, all of them. They're all changing. So, when I think of D, this is really D is a function of time. When I think of B, B is a function of time. L is also a function of time. There's this hidden function of time. So taking derivative of everything, what's the derivative of D squared going to be? 2D dd dt. Yes? No? The derivative of d squared, I claim, is 2d dt dt. Yes. Okay, a few people say yes. Remember, it's d is a function of t. What's the derivative of b squared? 2b db dt. That is the question. Equals derivative of L squared. 2L dL dt. If you don't know where these things are coming from now, and you see this question on the tests, that's not good. You should understand it now. You're not going to get an epiphany suddenly when the test comes. So, do you see where these terms are coming from? It's not magic. It feels like it sometimes. And it's not religion. You know, it's just like, you got to believe. You must believe. But no, these are really coming from somewhere. So, when we say d dt, that means the derivative of d with respect to t. So that's, okay, anyways, all right. What comes next? Plug in what we know. Okay, so let's talk about what we know. What is this 50? That's L. So L is 50. Okay, so we have 2 times 50. What is this 8? dL dt. Now, is it plus 8 or minus 8? And how do we know? What does the word extend tell you? It's getting longer. It's not contraction is getting shorter, extending is getting longer. So is it plus 8 or minus 8? Plus 8. So 2 times 50 times 8. That's this piece. Equals, okay. Blah, 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 blah. This 30, what is that? That's our distance from the building. So that's our capital D. So we have 2 times 30. What is this 5? d dt. Now, is that positive or negative? Pay attention to the signs. It's positive. When you move away from the building, what's happening to that length? It's getting farther away. It's getting longer. So it's a positive 5. Okay. 2 times 3 times 5. What is B? Do we really not know? Let's think about it. This L is 50. This D is 30. What's B? 40. 3, 4, 5 triangle. Now, what is dB dt? What we're solving for. Plug in what you know. Solve for what you don't. You can cancel some 2's. Let's say we have 150. Here's 160. So this becomes 40 dB dt. Sorry, not 160. This is 50 times 8 is 400. 30 times 5 is 150, so that's 250. And now divide. And oh, we have barely any space, but 250 over 40 is 25 divided by 4. So, are we moving up or down? Up. dB dt is positive, and so we're moving up the side of the building at 25 feet per minute. All right, that's it for today. We'll keep going for next time.